Good afternoon, ladies and gentlemen of Algebra Honors. Good to have Gabby back here today. She reports that she took and passed her driver's license exam, so that's a good thing. I'll be on the lookout for a new driver on the road. I'm sure she'll do great. Okay. Inverse variation. We're going to start on chapter 9. What does it mean for one variable to vary inversely as another variable? And so we're going to be talking about inverse variation. So we're going to have a discussion before working on some problems today. So we're going to investigate inverse variation. And the first example we're given here is one where if you have an area A of a rectangle with length L and W and width W given by the formula A equals LW. If you hold the width constant and allow the length to vary, then the area will vary also. So if W equals 2, then the equation related A and L is A equals 2L. And we say A is said to vary directly as L, and 2 is called the constant of variation. And a direct variation is recognizable for which features on a graph. And this goes back to your star tested concept. Pardon me?
Say it again.
What are the two main or some of the characteristics of a direct variation graph? Two things.
It's straight.
It's what?
Straight.
A line, right? Straight is a line. Yeah, is a line. And what else? What about that line?
Is that infinite?
That's it here.
You're positive?
So the line actually goes through the origin. Okay. So what this is, you have in this case A equals 2L, and what is the equation for slope-intercept form? Remember what that is? Mx plus b, right? Okay, this is what does it take to make this equation a direct variation equation? One thing. Yeah, so b has to equal 0. So if we just go ahead and make this 0, now we have a direct variation situation. So that's all it is, right? Now we go to another situation here where we say let the area of a rectangle be 12 square units. Complete the table which lists possible positive integer lengths and widths for the rectangle. Note that it doesn't matter if the width is less than, equal to, or greater than the length. So here, if we have the area of a rectangle be 12 units, the length is 1, the width is 12. So if we have a length of 2, what is our width going to be?
24.
Because so what it is, the question is, what times 2 equals 12? And what is that? 6. So we're developing an inverse variation. What we're doing, 3 times what equals 12? 4, 3, 2, and 1.
No, because the total is 12.
Yeah, so they multiply together equal 12. So what this is like length times width is equal to 12. And if we want to have W as the dependent variable, okay, we can see what that's going to be. Let's go over here to develop the situation. Okay, on the coordinate plane below, draw each of the rectangles having the lengths and widths in the table from step A. And here we have drawn in already the 1 by 12. And the second one that Bryce gave us was this 2 by 6, right? And the next one that someone else gave us, I don't know who it was a 3 by 4. And then we had a 4 by 3. Then we had a
6 by 2.
6 by 2. And finally, we had a 12 by 1. So that's what this one looks like. So, what we do is, it says, using the coordinate plane, draw a smooth curve through the upper right corners. So I'm going to take a chance and get my pen out here. A little bit wobbly, but all right, that's not so bad. Yeah, you can see a little wobble there, but that's all right. So next it asks, write an equation that gives W in terms of L. So what's our equation? W equals what? Remember, it's L times W equals 12, right? So W equals what?
12 over L.
12 over L. And so this is an example of an inverse variation function or equation. And for an inverse variation, we call that value 12 the constant of variation. Now, one thing that we talked about at the beginning of the year was we talked about parent functions of Algebra 2, and I think, if I recall correctly, one of the ones that we mentioned was f of x equals 1 over x. Do you remember that equation? Yeah, Addie says we did, right? So here, can you see that this function here is really just a what of this is called the reciprocal parent function. Reciprocal parent function. So what is this one here drawn compared to this one? In fact, I'm going to sketch this one right here. I'm going to sketch it in purple. So here's the parent function sketched right like this, right? So what relation do these bear to each other in terms that we've talked about at kind of toward the end of first semester? What kind of a graphical transformation do we call this?
It's a transition. No, horizontal stretch. Or lower test that stuff.
Okay, the way we called this a vertical stretch by a factor of 12. So really this is just a variation or a child of the parent function. And that's what we try to do in algebra. We try to use our parent functions and model them to real world situations. And that's one of the things we do in algebra. So you ask about real world uses. Yeah, we're going to talk about what some of them are here. And here's an example of sort of a generic function. You have x comma a over x. And it says to use the equation y equals a over x to solve functions. And by the way, this a is called a constant of variation. And in this prior work here, our constant variation was 12. Okay, and now we talk about end behavior. As x approaches infinity, y approaches 0. As, do we have as, let's look at this one. As x approaches negative infinity, f of x approaches what? Okay, this right here that I wrote, no, what I wrote here, who said 0?
Me.
It is 0, right?
Does it like supposed to straighten out?
Yeah, now this one here is really a trick question, but still I didn't fool Jay. Because in this graph here, you actually don't approach negative infinity, do you? But if you had, what happens is, when you look at x and y representing real world quantities, that means you're restricted only to quadrant 1. If you had y equals 1 over x unrestricted, then this would be true. But this particular one right here, you don't actually approach negative infinity, but you do approach, no. You do approach 0 as x approaches 0, right? And here is x approaching 0 and y is approaching positive infinity. So that's what that looks like.
So you flip it over, like, reflect it over?
Yeah, so what that looks like, what this looks like is this. And what Jay was talking about, correct me if I'm wrong, Jay, was this one right here. You're going to approach 0 as you approach negative infinity on the other side, that we're ignoring because we're restricting to real world situations here. Okay? So that's just kind of setting the table for what we're doing with inverse variation. And we're going to, and chapter 9 is pretty much on inverse variation, so we'll be working on that for a couple weeks. And let me get you your assignment sheet to be working on this. So what's going to happen in our examination of this, it's going to be the same type of transformations we were looking at for other functions we looked at. Okay. Now, one thing that you don't have on your paper that I have on mine is, what do you think? You don't have the resolution that I have on mine, is what it amounts to.
Mr. G's pants. Got all the resolution.
Yes, that's right. I have all the resolution. You got the copying dregs from the copying diminution of resolution.
Mr. G doesn't care, doesn't have to get us all individual stuff on. We're scurry.
Oh, I like that. But at least I got one of those Wacom writing tablets to help me make videos for class. I did that. Right.
Use it.
Right, I
Yeah,
did
Jay,
that.
you should sell the rest of the phones for some technology.
I tried. Anyway, so what it is, one is similar to that example problem we worked out with that constant variation of 12. So I want you to try to work that out and sketch this in on the first quadrant, and we'll talk about that in a couple minutes, all right? One thing that people did in other classes, like second period class, was they made a table and used that table to get values and work from there. So if we have a length of 2, what is our width going to be? 8. And if we have a width of 4, we have a length of 4. So then we have 8, 2, and 16, 1. Does that make sense? So, did you have trouble sketching that on your paper? A little bit, you did okay. But again, I have some advantages of resolution that you don't have. But what's a disadvantage I have? Yeah, hand steadiness. Part of it has to do with just my inabilities as an artist, but also just kind of if I was doing this on a regular non-glitchy pen, I'd probably be a little steadier. Yeah, so then this next one is going to be 8 by 2, right?
I see you go up there and do as good as Mr. G, Tony.
Yeah, Connor, keep going.
No, that's different.
So Mr. G, you never got your other tablet thing to work or anything?
Well, I did. Here's what happened. I tried to, and it really wouldn't work right on this one. So what I did is I said, no, I can't do that, but I still like to use it. So I use it for making my own videos over here. And the thing about it is that even with that other computer, when I do it, it doesn't produce sound because it uses like too much in the way of resources from the computer somehow. It would be the same on this one, a Windows 7. So it would mess up this computer just as much if it could be used on this one up here. So I've retired it to my personal use. And I have Miss Kelso is quite envious of me, because that's the thing she would like to have, because it's such a good, and it really will even do distinctive things. So what I do with the thing doesn't require the high quality of work that equipment is capable of. Does that make sense? I'm using a thoroughbred horse to haul a hay wagon. Does that make sense?
Yeah, if you're getting groceries in the Lamborghini.
Yeah, getting groceries in a Lamborghini, right? Or delivering pizza in a Lamborghini or something.
That's okay.
Oh, I shouldn't have talked about pizza. All right.
Transformer action. I have a Lamborghini.
So, let's go here. Oops, I didn't like that one as well. I gotta draw pretty steep, don't I? That's a little better. Okay. Oh, you ladies are pretty good at laughing at me. Because my wife is really nice to me that way too. She laughs at my jokes.
I didn't hear you, but I would laugh.
I was just making little sound effects as I drew it. That's all. Little squeaking sound effects, that's all. But I think that actually doesn't look too bad, really. But anyway, what is the equation for that curve? W equals 16 over L, right? So these are the inputs, these are the outputs. So there we have, 16 is our constant of variation. All right? So what I want to do, I don't really intend to get through all this today, but I want to kind of just start on this, and what I could do is just sort of work out number 3, and then maybe we can call somebody to work out number 4, maybe. Okay. I want to do that. So what it is, what you have, if y varies inversely as x, and y equals 8 when x equals 3. So what I have is I have x times y is going to be equal to 8 times 3, which equals 24. So then we can create an equation. We have y equals what? 24 over x. So we have this, and what is the value of y when x is 12? Well, we put y is equal to 24 over 12, so that's going to be equal to what? 2. So this is a real world situation, really, when you think of it. And if you look at the other problems, they are real world applications. A long time ago, I had a friend of mine, Craig, from my church, had an idea for a party, and what he did is he said we're going to have a pay-per-view fight that we were going to watch, but he was going to get his friends together, and what were the friends going to do to help with the pay-per-view fight?
Throw in some cash.
Yeah, pay for it, right? Actually pay for it. And I forget exactly what the cost of the pay-per-view was, but let's say it was $100, because I think it was probably about that, because that's a reasonable for an event like that, right? That's how they end up paying these prize fighter millions for their fight to do this. And I'm not a big fan of fighting, the professional fighting, but just as something to do. So he was able to get 20 of his friends to chip in. So what did we each have to pay for that?
40 bucks.
No, not 40 bucks.
The cost is $100, 20 friends,
$5 apiece.
$5 each, right? So what if we only had 10 people that did it? What would it be?
$10.
$10 each, right? And you can see if you do something like rent a bus to go to a cheerleading competition, right? And each of the cheerleaders pay for the bus, and and the costs are shared evenly between the cheerleaders. Is that going to affect how much each cheerleader pays to go to that competition? Yeah, have you ever done something like that before? Yeah, so you know that. So if you really think about it, it kind of makes sense, doesn't it? So really that's what we're talking about in these problems. So let's go ahead and look at 4. And what I want to do is I want to kind of, for our final problem for the day, I want to choose somebody to help with number 4. So we'll work number 4. I'll choose somebody in a short period of time. It could even be our new driver, Gabby. Who knows? I don't know if she's too happy about that, but how she's going to go. She'll be okay.
Yeah, it's just confusing when they miss a few.
Okay, here we go. So we're going to get our shuffling going here.
Who y'all thinking?
Right. I got 5. I did, I set it up, like the first one.
Okay, so how did you set that up? You said x times y,
Times y equals 10 minus 4.
10 times 4 you mean,
Or yeah, 10 times 4.
which equals 40.
Yeah.
Okay, so you have x, y equals 40, then what?
And then I simplified that to y equals 40 over, 40 over x, and then equals 2y. And then I simplified that into 40 over 8.
So,
Because the y equals 8.
so y equals 8, so
Y is 8.
so y equals 8, so 8 equals 40 over x. And then you solve for x.
Yeah.
Did you like cross multiply and divide?
I mean, I just kind of thought of it in my head. Really.
So you just mental math, x has to equal 5. Now I want to tell you something, that's a good solution by the way, and that's the way I did it, Bryce. I want to tell you, there's another, what happens at the end of the class period that we have. So sometimes you're the benefit of things I've learned from other students along the way. And what happened is Victoria in 7th period, when she solved this, she solved for x. So she wrote this as x equals 40 over y. And that helped us out in this instance because what she was being asked about solving for x, right? So she had this ready formula like that. So that's what Victoria did, which in this particular instance, okay, was not the way I did it, nor the way Bryce did it, but was kind of a helpful way of looking at it. But that's the good thing about an inverse variation thing is you can do that. Essentially, those variables are interchangeable, aren't they? So that's helpful. So that's some good work. We're going to leave it there, and I appreciate everybody's participation.
This is made in China.
Do we continue?